Now that all of our code is running fast and awesome, let's talk a bit more about memory and how it affects the performance in our system. Many programming languages that are known for being close to the hardware, or rather high performance, like C, C++, and Fortran, usually require programmers to manage memory themselves. Effectively, programmers are responsible for allocating a block of memory, and then sometime in the future, deallocating it when they're actually done using it. Since you define when and how much memory to allocate and free, the entire quality of managing memory depends on your skills and effectiveness. It's a lot of responsibility. And in reality, programmers aren't always the best at keeping track of all those bits and pieces of memory. Think about it. Product development is a muddy and crazy process, and often memory ends up not getting freed properly. These unliberated blocks of memory are called memory leaks, and they just sit around, hogging resources that you could use better or somewhere else. To reduce this chaos, stress, and sometimes big money losses caused by memory leaks, managed memory languages were created. The runtimes of these languages track memory allocations and release memory back to the system when it's no longer being needed by the application itself, all without any intervention from the programmer. This art, or rather science, of reclaiming memory in a managed memory environment is known as garbage collection. This concept was created by John McCarthy back in 1959 to solve problems in the Lisp programming language. The basic principles of garbage collection are as follows. Number one, find data objects in a program that cannot be accessed in the future. For example, any memory that is no longer referenced by the code. And number two, reclaim the resources used by those objects. Simple concept in theory, but it gets pretty complex once you've got 2 million lines of code and 4 gigs worth of allocations. Now think about it. Garbage collection can be really gnarly. If you've got some 20,000 allocations in your program right now, which ones aren't being needed anymore? Or better yet, when should you execute a garbage collection event to free up memory that isn't used?
These are actually very difficult questions, and thankfully we've had about 50 years worth of innovation to improve them, which is why the garbage collector in Android's runtime is quite a bit more sophisticated than McCarthy's original proposal. It's been built to be as fast and non-intrusive as possible. Effectively, the memory heaps in Android's runtimes are segmented into spaces based on the type of allocation and how best the system can organize allocations for future GC events. As a new object is allocated, these characteristics are taken into account to best fit what space it should be placed into, depending on what version of the Android runtime you're using. And here's the important part. Each space has a set size. As objects are allocated, we keep track of the combined sizes, and as a space starts to grow, the system will need to execute a garbage collection event in an attempt to free up memory for future allocations. Now, it's worth pointing out that GC events will behave differently depending on what Android runtime you're using. For example, in Dalvik, many GC events are stop the world events, meaning that any managed code that is running will stop until the operation completes, which can get very problematic when these GCs take longer than normal, or there's a ton of them happening at once, since it's going to significantly eat into your frame time.
And to be clear, the Android engineers have spent a lot of time making sure that these events are as fast as possible to reduce interruptions. That being said, they can still cause some application performance problems in your code. Firstly, understand that the more time your app is spending doing GCs in a given frame, the less time it's got for the rest of the logic needed to keep you under the 16 millisecond rendering barrier. So if you've got a lot of GCs or some long ones that are occurring right after each other, it might push your frame processing time over the 16 millisecond rendering barrier, which will cause visible hitching or jank for your users. Secondly, understand that your code flow may be doing the kinds of work that force GCs to occur more often, or making them last longer than normal durations. For example, if you're allocating a horde of objects in the innermost part of a loop that runs for a long time, then you're going to be polluting your memory heap with a lot of objects, and you'll end up kicking off a lot of GCs quickly due to this additional memory pressure. And even though we're in a managed memory environment, memory leaks can still happen, although they're not as easy to create as the other languages. These leaks can pollute your heap with objects that won't get freed during a GC event, effectively reducing the amount of usable space you have and forcing more GC events to be kicked off in a regular fashion as a result. So that's the deal. If you want to reduce the amount of GC events that happen in a given frame, then you need to focus on optimizing your app's memory usage. From a code perspective, it might be difficult to track down where problems like these are coming from, but thankfully, the Android SDK has a set of powerful tools at your disposal. Let's take a look.